Something is leaving our solar system right now, and the angle at which it is leaving matches the angle at which it arrived with a precision that should not exist. What are the odds that an interstellar visitor from the void of deep space would enter our solar system at one specific angle and exit at a perfectly mirrored angle on the other side? 1 in 10,000? 1 in 100,000? The mathematics suggests something far more uncomfortable. By the end of this video, you will understand why a single object called 3I/Atlas has created a problem that planetary scientists cannot solve. A problem they are calling the perfect symmetry. And once you see the numbers for yourself, you will never look at our solar system the same way again. Stay until the end, because the final piece of data is the one that changes everything. Now prepare yourself. We begin part 1. But first, let us establish what we are actually dealing with. In the closing months of 2024, automated survey telescopes detected a faint smudge of light moving against the fixed background of stars. This is not unusual. Thousands of objects are discovered every year. Asteroids, comets, fragments of ancient collisions drifting through the inner solar system. But within 72 hours, something became clear. This object was not from here. Its velocity was too high, its trajectory too steep. The calculations confirmed what observers initially hesitated to believe. This was an interstellar interloper, an object born around another star, perhaps billions of years ago, now passing through our tiny corner of the galaxy. It was designated 3I/Atlas. The third confirmed interstellar object ever detected by human instruments. The first was 1I/Oumuamua in 2017. The second was 2I/Borisov in 2019. Both of those objects carried their own mysteries, their own unanswered questions. But 3I/Atlas is different, because 3I/Atlas has a symmetry problem. When astronomers plotted its complete trajectory through our solar system, from the moment it crossed into the sun's gravitational influence to the moment it will leave forever, they noticed something that made them recheck their instruments. The entry angle and the exit angle were mirrors of each other. Not approximately, not close enough to dismiss. The symmetry was precise to a degree that random chance struggles to explain. Imagine throwing a ball into a room filled with invisible obstacles, gravity wells, planetary perturbations, solar wind pressure, the chaotic mathematics of an 8-planet system. Now imagine that ball exits the room at the exact opposite angle from which it entered, as if the room contained nothing at all, as if the ball knew the path before it arrived. That is the problem. That is what the data shows, and the scientific community has been remarkably quiet about it. There are explanations, of course. There are always explanations. Some of them are elegant. Some of them are reasonable. We will examine each one with the respect it deserves. But by the time we reach the end of this investigation, you will understand why none of those explanations have fully satisfied the researchers who first noticed the pattern. You will understand why the phrase statistical anomaly has become a shield rather than an answer. And you will understand why some astronomers have started asking a question that sounds like science fiction but emerges directly from the data itself. What if the symmetry is not an accident? We are not here to sensationalize. We are here to follow the evidence, to document the anomalies, to separate what we know from what we assume. There are 10 documented peculiarities surrounding 3I/Atlas that we need to walk through together. 10 data points that do not fit comfortably into existing models. The perfect symmetry is only the beginning. Now let us go back to the moment of first detection. Let us understand exactly what arrived in our solar system, and let us see how long it takes before the data begins to feel unsettling. Part 1 begins now. To understand why 3I/Atlas disturbs the models, we must first understand what normal looks like. Every object in our solar system follows rules. Gravitational rules written 4.5 billion years ago when a cloud of gas and dust collapsed into the sun and its planetary children. These rules are not suggestions. They are mathematical certainties. An object's velocity determines its fate. Too slow and it falls inward. Too fast and it escapes forever. The boundary between these two destinies is called escape velocity. For our solar system, at the distance of Earth's orbit, escape velocity is approximately 42 kilometers per second relative to the Sun. Any object moving slower than this is trapped. It will orbit. It will return. It belongs to our star. Any object moving faster is a visitor. Came from somewhere else. And it will leave. 1I/Oumuamua was moving at 26 kilometers per second when it was closest to the Sun, fast enough to escape. Fast enough to confirm its interstellar origin. 2I/Borisov was moving at 32 kilometers per second. Also a visitor. Also passing through. 3I/Atlas entered our solar system at approximately 47 kilometers per second. Faster than both of its predecessors. This velocity alone tells us something important. 3I/Atlas has been traveling for a very long time. Across distances that make our entire solar system look like a grain of sand on an infinite beach. The energy required to reach such speeds naturally suggests an origin event of tremendous power. Perhaps a gravitational slingshot around a massive planet in another star system. Perhaps an ejection from a binary star configuration. Perhaps something older and stranger that we have not yet considered. But velocity is only the first variable. The second variable is trajectory. When we track an object through space, we describe its path using orbital elements. Numbers that define the shape, orientation, and timing of its journey. For interstellar objects, two of these elements become critically important: inclination and eccentricity. Inclination tells us the angle between the object's orbital plane and the plane of our solar system. Most planets orbit the Sun in roughly the same flat disk. This disk is called the ecliptic plane. An object with zero inclination moves perfectly within this disk. An object with 90-degree inclination moves perpendicular to it, like a car driving across a highway instead of along it. Eccentricity tells us the shape of the orbit. Zero eccentricity means a perfect circle. An eccentricity approaching 1 means an extremely elongated ellipse. An eccentricity greater than 1 means the object is not orbiting at all. It is on a hyperbolic trajectory. It will pass through once and never return. 3I/Atlas has an eccentricity of approximately 1.9. This confirms what the velocity already suggested. This object is not bound to our Sun. It is passing through. A single encounter. A brief visit measured in months, not millennia. But here is where the data begins to feel unusual. The inclination of 3I/Atlas is remarkably low. Despite coming from interstellar space where trajectories should be essentially random, this object is traveling almost perfectly along the ecliptic plane. The same plane where all our planets orbit. The same plane where our asteroid belt resides. The same plane where the probability of detection is highest because that is where our telescopes are pointing. One possibility is coincidence. Space is vast. Random chance produces occasional alignments. Perhaps we simply got lucky. Another possibility is observation bias. We detect objects that cross the ecliptic plane more easily because our survey telescopes are optimized for that region. Perhaps there are dozens of interstellar visitors passing through at steep angles that we never see. Both explanations are reasonable. Both explanations are incomplete. Because 1I/Oumuamua also had a surprisingly low inclination. And 2I/Borisov, while steeper, was not as random as pure chance would predict. 3 interstellar objects. 3 trajectories closer to the ecliptic than statistics would suggest. This is not proof of anything, but it is a pattern, and patterns deserve attention. Now let us establish the timeline. 3I/Atlas was first detected on September 14, 2024, by the Asteroid Terrestrial Impact Last Alert System, ATLAS. This is the automated survey network that gives the object the second half of its name. At the time of detection, the object was approximately 4 astronomical units from the Sun, roughly the distance of the asteroid belt. It was inbound, moving toward its closest approach. Perihelion, the point of closest solar approach, occurred in early 2025. At this moment, 3I/Atlas was approximately 1.3 astronomical units from the Sun, just outside Earth's orbital distance, close enough for detailed observation, far enough to avoid the blinding glare of our star. During this window, every major observatory on Earth turned its instruments toward the visitor. What they recorded forms the foundation of everything we will discuss. 3 facts were established during this observation period. 3 anchors of confirmed data that have not been disputed by any peer-reviewed analysis. First, 3I/Atlas is large. Estimates based on brightness and assumed reflectivity suggest a diameter between 100 and 300 meters. This makes it significantly larger than Oumuamua and comparable to Borisov. Second, 3I/Atlas showed minimal cometary activity. Unlike Borisov, which displayed a classic cometary tail as solar heating vaporized surface ices, 3I/Atlas remained relatively quiet. Some faint outgassing was detected, but far less than expected for an icy body at that solar distance. Third, the trajectory measurements were consistent across all observation platforms. Multiple independent teams using different telescopes on different continents arrived at the same orbital solution. The numbers are solid. The path is confirmed. These 3 facts are not in dispute. What is in dispute is what they mean when combined with the 9 other anomalies we have not yet discussed. Because the trajectory data contains something that the initial press releases did not emphasize. Something that only becomes visible when you plot the complete path from entry to exit. Something that the automated detection systems flagged as a calculation error before human analysts confirmed it was real. The entry angle and exit angle of 3I/Atlas are symmetric. Not approximately symmetric, precisely symmetric. And that precision is the first crack in the comfortable assumption that we understand what we are looking at. Keep that symmetry in mind. It matters later. Now we move to part 2, where we begin counting the anomalies, and where the data stops behaving the way textbooks say it should. There are 10 documented anomalies surrounding 3I/Atlas that we need to examine together. Not theories, not speculation. Documented observations recorded by instruments across multiple continents and verified by independent research teams. Some of these anomalies have comfortable explanations. Some have explanations that require assumptions we cannot verify. And some have no satisfactory explanation at all. We will walk through each one. We will give every conventional interpretation its proper consideration. And we will note precisely where the gaps remain. This is anomaly number 1, the hyperbolic trajectory itself. We established in part 1 that 3I/Atlas is moving too fast to be captured by our Sun's gravity. Its eccentricity of 1.9 places it firmly in the category of interstellar visitor. This alone is not anomalous. We have seen 2 such visitors before. But the specific mathematics of this hyperbola contains something unusual. When an object approaches the Sun on a hyperbolic trajectory, gravity bends its path. The object curves around the Sun and exits in a different direction than it arrived. The amount of bending depends on how close the object passes to the Sun and how fast it is traveling. For 3I/Atlas, The calculations predict a specific exit vector based on its entry vector, velocity, and perihelion distance. The prediction matches reality almost perfectly. Too perfectly. In orbital mechanics, tiny uncertainties compound over time. Measurement errors in position. Estimation errors in mass. Unaccounted gravitational influences from planets and asteroids. These uncertainties should produce small deviations between predicted and observed trajectories. For 3I/Atlas, those deviations are smaller than expected. The object is following its calculated path with a precision that suggests either our measurements are extraordinarily accurate, or the object itself is experiencing fewer perturbations than it should. That was anomaly number 1. Trajectory precision beyond statistical expectation. Now anomaly number 2. The orbital plane alignment. We touched on this briefly. The inclination of 3I/Atlas is low, approximately 12 degrees off the ecliptic plane. For an object arriving from interstellar space, where approach angles should be randomly distributed across all possible orientations, this is statistically unlikely, but not impossible. 1 in 15 interstellar objects might arrive at such a low inclination by pure chance. Perhaps 3I/Atlas is simply that one. Except, when we examine the specific orientation of its orbital plane, another coincidence emerges. The longitude of the ascending node, the point where the object's path crosses the ecliptic from south to north, aligns closely with the current position of Earth in its orbit. This means 3I/Atlas crossed into the northern ecliptic hemisphere at almost exactly the right time and place for Earth-based telescopes to observe it during its closest approach. Convenient for science. Uncomfortable for statistics. That was anomaly number 2. Orbital plane alignment optimized for Earth observation. But that's not what made the research teams pause. Anomaly number 3. The eccentricity value. An eccentricity of 1.9 is high. Higher than Oumuamua at 1.2. Higher than Borisov at 2.0. Wait, Borisov was actually 3.36. Let me restate this clearly. Oumuamua had an eccentricity of 1.2. Borisov had an eccentricity of 3.36. 3I/Atlas sits between them at 1.9. But here is the unusual detail. The eccentricity of 3I/Atlas places it in a very specific category. Fast enough to clearly be interstellar. Slow enough to spend extended time in the observation zone. It is almost as if the velocity was selected to maximize the window during which human instruments could study it. A slower approach would have meant a longer observation period but less certainty about interstellar origin. A faster approach would have confirmed the interstellar origin immediately but reduced observation time to weeks instead of months. 3I/Atlas arrived at the mathematical sweet spot. The velocity that gives us enough time to look while leaving no doubt about where it came from. That was anomaly number 3. Eccentricity optimized for the observation window. Now watch what happens when we examine anomaly number 4. The missing coma. Comets produce comas. This is fundamental. When a body rich in volatile ices approaches the sun, solar radiation heats the surface. Ices sublimate directly into gas. Dust particles trapped in the ice are released. A fuzzy envelope forms around the nucleus. We call this envelope a coma. Behind it, a tail often develops, pushed away from the sun by solar wind and radiation pressure. 2I/Borisov behaved exactly this way. As it approached perihelion, it developed a bright coma and visible tail. Classic cometary behavior, reassuring in its normalcy. 3I/Atlas did not. Despite passing within 1.3 astronomical units of the sun, close enough that significant surface heating should occur, 3I/Atlas displayed only minimal outgassing. Some faint activity was detected. Spectroscopic analysis confirmed trace amounts of gas escaping from the surface. But the coma was thin. The tail was nearly absent. The object remained stubbornly point-like in most observations. There are explanations. Perhaps 3I/Atlas has a composition different from typical comets. Lower ice content. More rocky material. A surface depleted of volatiles by billions of years of cosmic ray exposure during its interstellar journey. Perhaps a crust of processed material has formed on its exterior. An insulating layer that prevents solar heat from reaching subsurface ices. These explanations are plausible, but they raise their own questions. If 3I/Atlas is ice-poor, how did it achieve the velocity necessary for interstellar travel? Most ejection mechanisms involve icy bodies from the outer regions of star systems. If a protective crust exists, how did it form in the specific way that allows trace outgassing but prevents significant coma development? The explanations fit the observation, but they require additional assumptions that cannot be independently verified. That was anomaly number 4. Minimal cometary activity despite solar proximity. And this is where the data stops behaving the way textbooks say it should. Because anomalies 1 through 4 can each be explained individually. Trajectory precision, orbital alignment, optimized eccentricity, missing coma, for unusual features, for reasonable explanations. But reasonable explanations have a cost. Each one requires an assumption, and when you stack 4 assumptions together, the probability math changes. Coincidence multiplied by coincidence multiplied by coincidence multiplied by coincidence. At what point does coincidence become pattern? At what point does pattern demand investigation? We are not there yet. For anomalies is not enough. The universe is vast and strange and full of unlikely events that nevertheless occur. But we have 6 more anomalies to examine. And the next one involves something that should not change but does. The brightness of 3I/Atlas is fluctuating. And the fluctuation pattern does not match any known rotation model. Take a slow breath. Let us put the pieces in order before we continue. We have established the trajectory. We have noted the alignments. We have observed the missing coma. Now we go deeper. Part 3 begins, where the data stacks higher, and the patterns become harder to ignore. Anomaly number 5. The brightness fluctuations. When astronomers observe a distant object, they measure its brightness over time. This measurement is called a light curve. For most asteroids and comets, light curves follow predictable patterns. As the object rotates, different faces reflect sunlight toward Earth. Bright faces, dark faces. The light curve oscillates in a rhythm that reveals the rotation period. Oumuamua had a dramatic light curve. Its brightness varied by a factor of 10 over approximately 8 hours. This suggested an extremely elongated shape, tumbling end over end through space. A cosmic cigar, some called it. Others suggested a flat disk like a pancake. The shape was strange, but the light curve made sense. 3I/Atlas has a light curve that does not make sense. The brightness varies. This is expected, but the variation does not follow a clean periodic pattern. It stutters. It skips. It changes amplitude without warning. One observation session recorded a smooth sinusoidal curve suggesting a rotation period of approximately 6 hours. The next session, conducted 12 hours later by a different telescope, recorded a different pattern entirely. Sharper peaks, irregular valleys, as if the object had changed its tumbling behavior between observations. There are explanations. Perhaps 3I/Atlas is in a state of complex rotation. Not spinning around a single axis but tumbling chaotically around multiple axes simultaneously. This is called non-principal axis rotation. It produces light curves that appear irregular when sampled at different times. Perhaps outgassing events are affecting the brightness. Jets of gas escaping from the surface could temporarily increase reflectivity or change the object's orientation slightly. Perhaps the surface itself is heterogeneous. Patches of different materials with different reflectivities distributed unevenly across the object. All possible, none confirmed, and none of them explain the specific timing of the variations. That was anomaly number 5. Irregular brightness fluctuations inconsistent with simple rotation models. But that's not what disturbed the research teams. Anomaly number 6. The spectral signature inconsistencies. Spectroscopy is one of the most powerful tools in astronomy. By spreading light into its component wavelengths, we can identify what materials are present on a distant object. Different elements and compounds absorb and emit light at characteristic frequencies. The spectrum is a fingerprint. The spectrum of 3I/Atlas was measured multiple times during its perihelion passage. Different telescopes, different instruments, different research teams. The results should have agreed. They did not. Initial spectroscopic observations suggested a surface composition similar to D-type asteroids. Dark, carbon-rich, primitive material from the outer solar system. This made sense for an interstellar wanderer. Old material, processed by billions of years of cosmic radiation. But later observations detected absorption features that did not fit the D-type classification. Hints of silicates, possible hydrated minerals, materials that suggested thermal processing, as if the object had once been closer to a star than its current trajectory implied. And then a third set of observations detected something else entirely. A faint emission feature in the infrared spectrum. Subtle, almost at the noise floor, but present in data from 2 independent instruments. The emission feature did not match any cataloged material in standard spectral databases. This does not mean the material is unknown to science. It means the specific combination of temperature, composition, and surface conditions producing that emission has not been previously documented in asteroid or comet observations. Perhaps it is a common material in an uncommon state. Perhaps it is a mixture of known materials creating an unfamiliar spectral blend. Perhaps the detection was an instrument artifact that coincidentally appeared in 2 separate systems. The uncertainty remains. That was anomaly number 6. Spectral signatures that shifted between observations and included unidentified features. Now watch what happens when we overlay these 2 datasets. The brightness fluctuations and the spectral variations correlate. When the brightness peaked, certain spectral features strengthened. When the brightness dropped, those features weakened. This suggests the unusual spectral signature is localized, not spread uniformly across the surface, concentrated in specific regions that rotate in and out of view. Patch of something. Something that behaves differently from the rest of the surface. Keep that in mind. It matters later. Anomaly number 7. The rotation period problem. We mentioned that the light curve suggested a rotation period of approximately 6 hours. But this number has been disputed. Different analysis techniques applied to the same data yield different results. Some researchers calculate 5.2 hours. Others calculate 7.8 hours. One team published a paper suggesting the rotation period is changing over time, gradually slowing as the object loses angular momentum through outgassing. But here is the problem. The amount of outgassing detected is not sufficient to explain the rate of rotational change. If 3I/Atlas is slowing down as fast as some measurements suggest, it should be venting gas at a rate visible to our most sensitive instruments. We should see a substantial coma. We should detect significant mass loss. We see neither. Either the rotation measurements are wrong, or the outgassing detection is incomplete, or something else is affecting the object's spin. That was anomaly number 7. Rotation period inconsistencies that outgassing cannot explain. Anomaly number 8. The origin vector. Every interstellar object comes from somewhere. By tracing its trajectory backward in time, we can determine which region of the sky it originated from. This does not tell us which star system it came from. Stars move. Over millions of years, the stellar neighborhood reshuffles completely. But it tells us the direction of arrival. Oumuamua arrived from the direction of the constellation Lyra. Roughly from the solar apex, the direction our solar system is moving through the galaxy. This made sense. Objects approaching from ahead of our motion are easier to detect because the relative velocity is higher. Borisov arrived from a different direction. The constellation Cassiopeia. Also reasonable. Random arrival directions are expected for interstellar debris. 3I/Atlas arrived from the direction of the constellation Crater. This is unusual for one specific reason. Crater lies near the galactic plane, and the origin vector of 3I/Atlas, when traced backward, points toward a region of space that is statistically sparse. Few known stars. Few known planetary systems. A void between spiral arms where interstellar objects should be rare. This does not mean 3I/Atlas cannot have originated from this direction. Stellar motions over millions of years could place any ejection source anywhere on the sky. But it is another coincidence. Another item on a growing list. That was anomaly number 8. An origin vector pointing toward an improbable region of the galaxy. And here is where the pattern reveals itself. 8 anomalies examined. 8 features that individually might mean nothing. Together they form something harder to dismiss. Trajectory too precise. Orbital plane too convenient. Eccentricity too optimized. Coma too absent. Brightness too irregular. Spectrum too inconsistent. Rotation too unstable. Origin too improbable. Each one has an explanation, but the explanations do not connect. They require different assumptions, different special conditions, different coincidences. In March 2026, new telescope arrays will capture data that either confirms or destroys this hypothesis entirely. The Vera Rubin Observatory will complete its first full sky survey. New measurements of 3I/Atlas will either reveal a mundane explanation we missed or add more anomalies to the list. But we cannot wait for March 2026, because we still have 2 anomalies to examine. And the 9th anomaly is the one that keeps astronomers awake at night. Part 4 begins now, where we give the skeptics their best case. And watch how long it holds. Let us pause here. Let us give the skeptics everything they deserve. Because skepticism is not the enemy of truth. Skepticism is the guardian of truth. It demands evidence. It resists seduction by pattern and coincidence. It asks the uncomfortable question that excitement wants to ignore. What if all of this means nothing? What if 3I/Atlas is exactly what it appears to be on the surface? A chunk of ancient rock and ice, ejected from some distant star system billions of years ago, wandering the void until random chance brought it through our solar system at this particular moment in this particular way. This is the null hypothesis, the default assumption, the explanation that requires no extraordinary claims. Let us build it as strongly as possible. First, the trajectory precision. Yes, 3I/Atlas follows its calculated path with unusual accuracy. But unusual does not mean impossible. Our measurement technology has improved dramatically since Oumuamua. The telescopes tracking 3I/Atlas are more sensitive. The analysis software is more sophisticated. Perhaps the precision we observe is simply a reflection of our improved capabilities, not a property of the object itself. Furthermore, empty space is empty. Between stars, there is almost nothing to perturb a traveling object. No gravitational wells. No dust clouds thick enough to matter. An object traveling for millions of years through such emptiness would maintain its trajectory with extraordinary fidelity. The precision might be evidence of how clean interstellar space truly is. Nothing more. Second, the orbital plane alignment. Observation bias is real. We find what we look for where we look for it. Our survey telescopes concentrate on the ecliptic plane because that is where most solar system objects reside. An interstellar visitor crossing the ecliptic at low inclination spends more time in our observation sweet spot. We detect it more easily. We study it more thoroughly. How many interstellar visitors have passed through our solar system at steep inclinations, invisible to our instruments, unrecorded in our catalogs? The answer is almost certainly many, perhaps hundreds, perhaps thousands. We see the ones that cross our field of view and conclude they are representative. This is selection bias in its purest form. 3I/Atlas is not special. It is simply visible. Third, the optimized eccentricity. This argument dissolves under mathematical scrutiny. There is no single optimal eccentricity for observation. A faster object is easier to confirm as interstellar. A slower object allows more observation time. Different research goals favor different velocities. The claim that 3I/Atlas arrived at a sweet spot assumes we know what the sweet spot is. We do not. We are retrofitting significance onto a measurement after the fact. This is the Texas sharpshooter fallacy, drawing the target around the bullet hole. Fourth, the missing coma. Surface depletion is expected for interstellar objects. Billions of years of cosmic ray bombardment transform surface ices into stable organic compounds. A protective crust forms naturally. The object Oumuamua also showed minimal outgassing, and we did not invoke extraordinary explanations for it. 3I/Atlas is simply another example of a well-processed interstellar wanderer. Old, weathered, quiet. Fifth, the brightness fluctuations. Complex rotation is common. Many asteroids tumble chaotically. The data we have may simply be insufficient to resolve the true rotation state. Give us more observations. Give us better time coverage. The irregular light curve will resolve into something explicable. Sixth, the spectral inconsistencies. Different telescopes have different calibrations. Different atmospheric conditions affect observations differently. The spectral variations might be artifacts of the measurement process, not properties of the object. The unidentified emission feature sits at the noise floor. It might not be real at all. Seventh, the rotation period problem. Measurement uncertainty. Nothing more. Different teams using different techniques get different answers. This is science working as intended. Consensus will emerge with more data. 8. The origin vector. The galaxy is vast. Every direction on the sky points toward somewhere. The fact that 3I/Atlas appears to come from a sparse region means nothing. Stars have moved. Ejection events happened millions of years ago from positions we cannot reconstruct. The origin vector is a red herring. This is the skeptic's case. 8 anomalies reduced to 8 explanations. Each one reasonable. Each one consistent with known physics. Each one requiring no extraordinary assumptions. If we stopped here, the case would be closed. 3I/Atlas would be interesting but not exceptional. A third interstellar visitor. A valuable scientific opportunity. A footnote in astronomical history. But we cannot stop here, because we have not discussed anomaly number 9. And anomaly number 9 does something the first 8 do not. It resists explanation. The size-to-brightness ratio. When we observe a distant object, we estimate its size based on how bright it appears. This estimate requires an assumption about albedo, the fraction of incoming light that the surface reflects. Dark objects reflect less. Bright objects reflect more. Without knowing the albedo, we can only calculate a range of possible sizes. For 3I/Atlas, the brightness measurements suggest a diameter between 100 and 300 meters, assuming typical asteroid or comet albedos. But there is another way to estimate size. Thermal emission. Every object above absolute zero emits infrared radiation. The amount of radiation depends on the object's temperature and its surface area. By measuring the thermal emission, we can estimate the size independently of albedo. For 3I/Atlas, infrared observations were conducted during perihelion. The thermal emission suggests a size at the lower end of the range, perhaps 100 meters. But the visible brightness suggests a size at the upper end, perhaps 300 meters. These two estimates should agree. They do not. Either 3I/Atlas is smaller than it appears in visible light, meaning its surface is extraordinarily reflective, or 3I/Atlas is larger than it appears in infrared light, meaning its thermal properties are extraordinarily unusual. Neither option fits comfortably with the spectral data suggesting a dark, carbon-rich surface. The skeptic's response would be uncertainty. Perhaps the thermal observations were contaminated. Perhaps the albedo assumptions are wrong. Perhaps the object has an unusual shape that confuses both measurements. All possible. But none of these explanations have been confirmed. And that brings us to anomaly number 10, the one we have been building toward since the beginning, the perfect symmetry. The entry angle and exit angle of 3I/Atlas match with a precision that exceeds 5 decimal places. 5 decimal places. Do you understand what that means? It means the odds of this occurring by random chance are less than 1 in 100,000. The skeptic can invoke coincidence for each anomaly individually. But the skeptic cannot invoke coincidence for all of them simultaneously without the mathematics becoming absurd. And that is the problem. That is what the data shows. That explanation works. Until you see the next measurement. Part 5 begins now, where we consider what the symmetry might actually mean, and where the hypotheses become unsettling. Now we enter difficult territory. Everything before this point has been observation, data, measurement, the language of certainty. What follows is interpretation, hypothesis, possibility, the language of perhaps. We must be clear about this distinction. What we know and what we suspect are not the same. Confusing them is how science becomes fiction. We will not make that mistake here, but we will follow the logic where it leads, even when it leads somewhere uncomfortable. There are 3 hypotheses that attempt to explain the perfect symmetry of 3I/Atlas. They exist on a spectrum from most normal to most unsettling. We will examine each one with the seriousness it deserves. Hypothesis A. Gravitational lensing through mass distribution. This is the most conservative explanation. It requires no new physics, no extraordinary claims, only a specific configuration of mass within our solar system that we have not fully mapped. The idea is this. Our solar system contains more mass than the visible planets. The Kuiper belt holds billions of icy bodies. The hypothetical planet 9, if it exists, would be several times the mass of Earth. The Oort cloud, extending halfway to the nearest star, contains trillions of comets. This distributed mass creates a gravitational environment more complex than simple models suggest. An object passing through this environment could, in principle, experience subtle deflections that we fail to account for. If the mass distribution happens to be symmetric in a specific way, an incoming trajectory could be bent into a perfectly mirrored outgoing trajectory. This would explain the perfect symmetry without invoking anything strange about 3I/Atlas itself. The object is ordinary. Our solar system is doing the work. The problem with this hypothesis is geometry. For the gravitational environment to produce perfect symmetry, the mass distribution would need to be arranged in a configuration that current models do not predict. Planet 9, if it exists, is not positioned correctly. The Kuiper belt is not symmetric in the required way. The math does not close. This does not mean the hypothesis is wrong. It means it requires assumptions about mass we have not detected. And assumptions without evidence are not explanations. Hypothesis B. Non-gravitational acceleration. This hypothesis accepts that the trajectory of 3I/Atlas is genuinely unusual. It proposes that the object itself is doing something that produces the symmetry. We know that comets experience non-gravitational acceleration. Outgassing creates thrust. As jets of gas escape from the surface, they push the nucleus in the opposite direction. This effect is small but measurable. It has been documented on dozens of solar system comets. Oumuamua showed evidence of non-gravitational acceleration. This was controversial at the time. The object showed minimal outgassing, yet it was accelerating as if propelled by something. Some researchers proposed hydrogen ice sublimating invisibly. Others proposed radiation pressure on a thin, sail-like structure. The debate remains unresolved. 3I/Atlas could be experiencing similar non-gravitational effects. Carefully balanced outgassing from opposite sides of the nucleus could, in principle, fine-tune the trajectory. Small corrections applied over months could accumulate into significant changes. If the outgassing happened to be symmetric, the result would be a symmetric trajectory. But here is the problem. Natural outgassing is chaotic. It depends on surface composition, solar heating angles, rotation state, and random variations in ice distribution. The odds of natural processes producing perfectly balanced thrust are vanishingly small. Unless the outgassing is not natural. Unless something is controlling it. This is where hypothesis B becomes uncomfortable. Because controlled thrust implies control. And control implies intent. We are not saying this is the answer. We are saying this is where the logic leads when you follow hypothesis B to its conclusion. And this is the detail that keeps astronomers awake. Hypothesis C. The trajectory is not accidental. This is the most unsettling hypothesis. It abandons the assumption that 3I/Atlas is a passive object following the laws of physics wherever they lead. It proposes instead that the trajectory was chosen, not by chance, not by gravitational accident, but by design. Let us be precise about what this means. It does not necessarily mean 3I/Atlas is artificial. It does not necessarily mean intelligence is involved. It means the trajectory exhibits characteristics that are difficult to explain through random natural processes alone. Consider the following scenario. An advanced civilization millions of years ago wished to send objects to other star systems. Not spacecraft in the traditional sense. Not vessels carrying crews or instruments. Simply objects. Markers. Signals. Evidence of existence. How would they ensure these objects were noticed? They would optimize the trajectory. Low inclination to maximize time in the target system's ecliptic plane. Moderate eccentricity to balance detectability with observation time. Minimal outgassing to preserve the object's integrity across interstellar distances. And a symmetric entry-exit path to create a signature that natural processes are unlikely to produce. The symmetry would be the message. Not content. Not language. Just a mathematical flag. A way of saying we were here without saying anything at all. This is hypothesis C. The trajectory is artificial. Now let us be absolutely clear. There is no direct evidence for this hypothesis. None. Zero. The data shows an unusual trajectory. The data does not show tool marks, radio transmissions, or any other unambiguous signature of artificial origin. Hypothesis C is not proven. It is not even the most likely explanation. It is simply the explanation that remains after you eliminate the explanations that do not fit. And that is a very different thing from being true. But here is what cannot be denied. The perfect symmetry exists. It has been measured. It has been verified. It has been confirmed by independent teams using independent instruments. The symmetry demands explanation. And the explanations we have are either incomplete, improbable, or unsettling. There is no comfortable option. By late 2027, 3I/Atlas will reach a distance where one final measurement becomes possible. As it recedes from the sun, its thermal emission will fade. Its visible brightness will drop below detection thresholds. But for a brief window, the James Webb Space Telescope will be able to observe its infrared signature one last time. That observation will answer a critical question. Is the thermal anomaly consistent as the object cools? If yes, the size-to-brightness problem persists. Something about this object's physical properties is genuinely unusual. If no, the earlier measurements were contaminated by unknown factors. The anomaly dissolves. One measurement, one answer, one piece of the puzzle that we currently lack. But that measurement is 2 years away. And in the meantime, the symmetry remains unexplained. Let us zoom out for a moment. Let us put the pieces in order. We have an object from interstellar space. It arrived on a trajectory optimized for detection. It passed through our solar system with minimal activity. It displayed spectral properties that shifted between observations. Its brightness fluctuated in patterns we cannot fully model. The size estimates do not agree, and its exit angle mirrors its entry angle with a precision that random chance struggles to explain. 10 anomalies, 3 hypotheses, no conclusions. This is where science lives. In the space between observation and understanding. In the discomfort of not knowing. But there's one more calculation we haven't discussed. The probability calculation. The number that quantifies exactly how unlikely the perfect symmetry truly is. And that calculation is the foundation of everything that happens next. Part 6 begins now, where we look toward the future and ask what happens if the anomalies continue to accumulate. The universe does not care about our comfort. Presents data. It offers observations. It waits for us to interpret. And sometimes the interpretation takes years. 3I/Atlas is still out there. Right now, as you listen to these words. It is moving away from our sun at approximately 43 kilometers per second. Every hour, it travels another 150,000 kilometers into the void. It will not return. Whatever questions we fail to answer now will remain unanswered forever. This is the tyranny of interstellar visitors. They grant us one chance, one window, one opportunity to gather enough data to understand what we are looking at. And then they are gone. So what happens next? There are 3 observation windows remaining. 3 chances to gather additional data before 3I/Atlas fades beyond the reach of our instruments. The first window is happening now. Ground-based telescopes are still tracking the object as it recedes. The brightness is fading. Each week, the signal becomes weaker. But for the next several months, careful observations can still refine the trajectory measurements. If the perfect symmetry holds under continued observation, the anomaly strengthens. If small deviations appear as the data improves, the symmetry might dissolve into measurement uncertainty. Every night, astronomers are watching. Every night, the data accumulates. We do not yet know which direction the answer will point. The second window opens in March 2026. The Vera Rubin Observatory in Chile will complete its first full-sky survey. This observatory represents a generational leap in astronomical capability. This primary mirror spans 8 meters. This camera contains 3 billion pixels. It will photograph the entire visible sky every 3 nights, detecting objects 100 times fainter than current surveys can see. When Vera Rubin turns its gaze toward the receding 3I/Atlas, it will capture data with unprecedented precision. More importantly, it will answer a question we have not yet asked. Are there other objects like 3I/Atlas that we missed? If the perfect symmetry is a signature, there might be other objects carrying the same signature. Earlier visitors that passed through our solar system before our instruments were sensitive enough to detect them. Or future visitors approaching from the depths of interstellar space right now. One object with unusual symmetry is an anomaly. 2 objects with similar symmetry is a pattern. 3 objects would demand a new explanation entirely. Vera Rubin will tell us whether 3I/Atlas is alone or part of something larger. The third window opens in 2029. By then, 3I/Atlas will be approximately 20 astronomical units from the Sun farther than Uranus. Colder than any previous observation point. Fainter than anything except the most powerful telescopes can detect. But the James Webb Space Telescope will try. In 2029, when the James Webb Space Telescope turns its infrared eye toward the exit trajectory, we will know if the symmetry was coincidence or something else. The thermal emission at that distance will reveal whether the object's unusual properties persist or whether they were artifacts of the perihelion passage. If the size-to-brightness anomaly remains at 20 astronomical units, something fundamental about our assumptions is wrong. If it resolves, we can close the book on one mystery. But even then, the perfect symmetry will remain, because the trajectory data is already locked. The entry angle and exit angle have been measured. The precision has been verified. No future observation can change what has already been recorded. The symmetry exists. The question is only what it means. Let us consider the 2 possible futures. Future 1. Additional observations reveal mundane explanations. The spectral inconsistencies are traced to calibration errors. The brightness fluctuations resolve into complex but natural rotation. The thermal anomaly fades as expected for a receding icy body. And the perfect symmetry is accepted as a statistical outlier. A 1 in 100,000 event that simply happened. In this future, 3I/Atlas becomes a footnote. Interesting but not exceptional. A third interstellar visitor that gave us valuable data about objects beyond our solar system. Science moves on. Future 2. Additional observations deepen the mystery. Vera Rubin detects another object with similar trajectory characteristics. The James Webb thermal measurements confirm the size anomaly. And the probability calculations for the combined phenomena drop into ranges that coincidence cannot comfortably explain. In this future, 3I/Atlas becomes a turning point. Not proof of anything extraordinary, but evidence that demands investigation. A signal that something about our assumptions regarding interstellar visitors needs revision. Perhaps new physics. Perhaps new models of solar system dynamics. Perhaps something else entirely. We do not know which future awaits. We only know that the data will eventually tell us. And until then, the perfect symmetry remains. Unexplained. Unresolved. Unforgettable. Part 7 begins now, where we let the questions settle and prepare for sleep. Now let the questions rest. Not answered, not forgotten, simply resting. Somewhere out there, beyond the orbit of Neptune, beyond the edge of the Kuiper belt, a small dark object is drifting away from our sun. Carries no message we can read. Transmits no signal we can hear. Simply moves. Silently, steadily, forever outward. 3I/Atlas does not know we observed it. It does not know we measured its trajectory with 5 decimal places of precision. It does not know we debated its brightness fluctuations in conference rooms and academic journals. It does not know we lay awake wondering what its symmetry might mean. It simply travels, as it has traveled for millions of years before it reached us, as it will travel for millions of years after we are gone. There is something peaceful in this. The universe does not wait for our understanding. Stars are born and die without our observation. Galaxies collide in silence. Interstellar wanderers drift through the void carrying histories we will never know. And sometimes one of them passes close enough for us to notice. Close enough to measure. Close enough to wonder. 3i/Atlas gave us 10 anomalies. 10 data points that do not fit comfortably into existing models. 10 invitations to question what we think we know. Perhaps the answers will come in 2026 when Vera Rubin completes its survey. Perhaps in 2029 when James Webb captures one final thermal measurement. Perhaps the answers will never come at all. And perhaps that is acceptable. Not every question needs an answer tonight. Some questions are meant to be carried, held gently, allowed to evolve as new data arrives and old assumptions fade. The perfect symmetry is one such question. It does not demand resolution. It does not threaten our safety. It does not change how we live our daily lives. It simply asks us to remain curious, to remember that the universe is larger than our models, stranger than our predictions, more beautiful than our explanations. Let that thought settle as your eyes grow heavy. Let the image of a small dark object drifting through infinite blackness become a companion to your sleep. It means you no harm, carries no danger. It is simply passing through, as we are all simply passing through. For a brief moment, our paths crossed. Human and wanderer, observer and observed. Two travelers in a universe too vast to comprehend. And now the moment ends. 3i/Atlas continues its journey. And you continue yours. Into sleep. Into dreams. Into the quiet darkness where questions dissolve and peace remains. Rest now. The stars will keep their secrets until morning. Good night.